Joey, and Severine, who will present the work today. And then we also have Fangyu from Cambridge, who I think is on the call with us today. And then we also have Joachim and me on the paper. And this is a novel method to actually produce a controllable text generation method. There has been some methods proposed in the literature. I guess you're going to cover those. But this is the new stuff, much better than before. And with that, I will leave the word to you guys. Just first, a practical thing. So usually when we have these seminars, we go for the online audience first during the discussion. But today we will actually start with the room here, since we are all here, right? And then after that, I will go to the online crowd. So we do the same thing. If you're online, you have questions, write in the chat, and I will keep an eye open for that. And then you can just raise your hand, and especially you guys here also raise. Great. So with that, who's first? Okay, cool.
Thank you for the introduction. Okay, so before diving into the controllable text generation, let's briefly cover what text generation is. So large causal language models like GPT have been trained on immense masses of text. And it's trained using the next token prediction objective. So it can look something like this. If we have the text, a cat sat on the mat, and we give the model the input, a cat sat on D, it's trained to predict mat. And after being trained on masses of text, you can use it for inference and generate text. So what you do here is to give it a context, in this case, the word A, and then it can process this token position and output distribution over its vocabulary. Then we can sample a word from this distribution, and in this example we have cat. And then we move this generated token to the input. And then in the next iteration we have a cat as input. And we can continue this process to generate an entire text. And a real example of this is with GPT-J, a Luther AI 6 billion parameter model. Here I prompt the model with Harry, Ron, and Hermione went over to Hagrid and asked. And then it continues with this entire text. So it continues with him if he had seen anything. No, he said, but I heard something. What? Asked Harry. I heard a noise, said Hagrid. It sounded like a giant was trying to get out of the castle. That's impossible, said Ron. The castle is too well guarded. I know, said Hagrid, but I heard it. So we can clearly see that they are capable of generating really interesting text. But notice how we can't steer it here. So we give it the initial context and then it rambles on. So what if we want to steer it towards some sentiment or some topic or something? So this is where controllable text generation comes in. And a step towards this is AI Dungeon. So this is a text-based story game that uses GPT. So when you go to their website, it goes something like this. You select a genre, a character, and a name. And in this case, I want a fantasy story where I'm a character named Buttercup. Sorry, a fairy named Buttercup. So we get the initial story, and it goes like this. You are Buttercup, a fairy living in the kingdom of Larian. You live in a fairy realm hidden under a grassy hill near the castle. Your skin is a light tinge of blue, your wings sparkle in the sunlight, and you are very small and good at hiding. You are fascinated by humans and love to watch them from their flowers where you blend in. While you are hiding, suddenly a handsome prince comes riding on his horse towards the flowers. You can't stop staring. You have never seen a human before, and you think he looks beautiful. And here you get to interact in the story. So here you can choose to make your character do something, say something, or continue narrating the story. And here I chose to say, hey, slow down. And then GPT continues the story. And then you go back and forth like this to generate the story together with GPT. So we can see that this is a really good example of entertainment by using these language models. And it could get even more fun if you can control it even better. So when looking at other methods for controllable text generation, we divide them into 3 different categories. we have first training objectives, where you fine-tune your language model towards some task of controlling the model. And then we have decoding strategies, which is more plug and play. So you don't have to fine-tune it at all. You just alter the model during inference. And lastly, we have prompting, where you just tell the model what you want it to do. And this may sound simple, but it's an entire field of its own. So an example of prompting, continuing on this Harry Potter example. So in this zero-shot setting, I start with a sentence that describes the task, which is the next sentence includes the words and angry and Dumbledore. And then I give the previous context and hope that it manages this task. We can see that it failed. It just said him what had happened. So what you can do here to improve the performance is to move over to the few shot setting. So here we provide 4 examples. In each example, we first have the task description and the target words, and then a sentence that completes the task. And then after that, we can insert our previous prompt. And we can see here that it managed to write why Dumbledore was so angry. And for decoding strategies, first we have keyword to text, which skews the vocabulary distribution during inference towards some keywords and its semantic neighbors. So if we have the keyword look, it will then skew the probability distribution to increase the probability for look, and also to its semantic neighbors. So for example, see and watch. Next up, we have PPLM, plug-and-play language models. So in this case, you have a small attribute model, which handles the task that you want it to do, and it steers the entire language model. So we have, in this case, the small mouse is steering the large language model, which is the elephant. And it's not only just skews the distribution, but it also alters the hidden states within the model through the gradients. And for training, we have a baseline which we have used in our experiments, which is KG-BART. And KG stands for knowledge graph. So BART is a encoder-decoder model. And it's in KG-BART, we fine-tune BART towards these controllable tasks. And it's not just BART, but also augmented with knowledge graphs. To formulate the task for our experiments, we have used CommonGen, which is a public data set that contains target words and reference text. So the task for models are to use these target words and generate text that includes these target words, but also to be similar to the reference text. And typically you measure your similarity to this reference text by using some text overlap metrics, such as BLA score. We don't believe this is suitable for this task because there's a lot of different sentences you can generate using these target words, and we don't find it suitable to punish the model for being creative in another way. So we scrap those and formulate the objective as generate high quality text, including the target words. But how can you evaluate high quality text? And looking at the literature, we see, for example, Öhman et al. That does a survey on this and argues that it's difficult and inconsistent throughout the field. And also that one metric is not enough. And to remedy this as much as we can, we use multiple automatic metrics and also human evaluation to complement it. So for automatic evaluation, first out we have perplexity, which is an indicator of language fluency. So here we use a larger language model to evaluate the generated text. And the perplexity is defined as the exponentiated average negative log likelihood of the generated sequence. And the probabilities here are calculated using this GPT-2 Excel. So we can see for 2 example sentences, we have all the dogs were playing in the park, and a slightly worse sentence, all the dogs had playing in the park. And if we calculate the perplexity, we see that the better sentence gets a lower perplexity. So a lower perplexity is better. However, there are problems with perplexity, as repetitions like this tends to get really low perplexity. But nevertheless, we find perplexity to be a really good language fluency indicator, but you should be careful not to rely on it alone. Then we have self-blur, which is a syntactic diversity metric. So to calculate this, if you have a list of generated sentences or texts, you focus on one at a time and use the other texts as references. And then you take the blur score of this, and you do this for all of the sentences, focusing at one at a time, using the others as references to get all these blur scores, which is an n-gram-based similarity score. And then you take the mean of those to get your self-blur diversity score. And lastly, we have coverage, which is the target word inclusion rate. And in this example, so we have the target words dog, park, and ball, and the generated text is the dogs are running around in a park. And we can see that 2 out of the 3 words are included here, meaning that the coverage is 66%. And the model's final coverage then is the sample average over all the generated text. So to remedy shortcomings of automatic evaluation and to really get a hint of how fluent a model is, or how good it is at understanding the world, or we evaluate it using common sense. So we ask evaluators how much the generated text makes sense. And we try to follow all the guidelines here to use multiple annotators and get high inter-annotator agreement and clear instructions and so forth. So if you have a generated text, the ice cream truck finally arrived and put the lake on fire. We then ask the evaluators, does this sentence make sense? And then they can then answer yes, partly, and no, which translates to the scalars 1, 0.5, and 0. So we have 5 annotators per sample, and doing it this way, we can quantify the common sense metric of a model. So our baseline results for CommonGen. In our experiment settings, we have 2 parts. We have free text, which allows the model to generate up to 32 tokens. And we have a single sentence, where the model can only generate 1 sentence. And then for each column, we have one of these metrics, with an arrow indicating the direction of performance. So for example, with coverage, the upwards arrow means that the higher coverage is better. Starting with GPT-2 large prompting, we see a coverage of 72%, a perplexity of around 16, self-blur 56, common sense 68. Comparing this to single sentence, GPT-2 large prompting, we see a slightly lower coverage and a much higher perplexity. And this makes sense because the model has fewer words to fit these target words into, and also a shorter sentence typically has a lot higher perplexity. And here's an example of GPT prompting. So we have the target words dog, leash, sidewalk, and walk. And it generated the dog was walking on the sidewalk. So it's a quite good text, but it misses 1 word. Then we have PPLM, which gets terrible coverage, but really good common sense and also quite good perplexity. And we can see that it completely ignores the task, but it writes some weird stuff, but still fluent language. And then we have keyword to text, which is kind of the opposite. It manages the task quite good, but gets quite high perplexity and low common sense. And an example here is this one. So we can see that it really handles the task, but doesn't write really good text. Oh, and notice here that PPLM and keyword to text are not part of the single sentence setting. And this is because they are designed to generate up to some amount of tokens. And we could, of course, cut it at the first sentence, but we don't deem it fair since maybe it was planning to include it right after the dot or something. So those are only included in the free text. And the opposite holds for KG-BART, which is trained to generate only 1 sentence. So we can see that KGBART is really good at all the metrics, and it makes sense because it's trained on this very task. And an example here is a dog walks on a leash on a sidewalk. So a quite boring sentence, but it manages well. Yeah, over to you.
Okay, so now Joey has given like an overview over all the baselines we have and like the field of controllable text generation. But we believed within the paper that there's still like a part missing in the evaluation of controllable text generation. So that's why we contributed also with a data set in the paper. And to give a bit more insight why we think there is one missing, I will start with the AI dungeon example that Joey gave. So you have about the buttercup fairy. I won't read it again, but then you also, so the goal of AI dungeon is you have some input of the user, and then you want to input this into the story, but of course your story also has to follow the context and not only the input that you give. For example, here we were talking about the fairy and she likes to watch people from their flowers. So it's always good that in the continuation of a story, this also comes back. So it's kind of important that algorithms can take context and input into account. And currently we only have in our data set just 3 words, and then we ask them, give a sentence containing these 3 words. But in the best case scenario, we also have like a sentence that gives like a little bit of a, makes it more likely to get in the next sentence these 3 words. And then you have like, and then you can evaluate your algorithm both on context and including the words. So in this case, given the words hand soap and wash, you could have the context. 5 minutes ago, Jacob went into the bathroom, and then it would be really good if the algorithm was able to make in the bathroom, he washed his hands with soap, because it's like including all the words and it also including the context. So what we did is we took the CommonGen data set. We only kept the so we only took the test part because it's a quite big data set, and we took all the concepts of that data set. We went to a crowdsourcing place like Amazon Mechanical Turk, and we asked people, please create like some sentences, some context, such that it's very likely that the next sentence will continue those 3 words or 4 words or 5 words. And then we quickly went through it manually to see if it's like kind of acceptable what was given as a context. So conclusion, we now have data set. So the original CommonGen you see at the top only has like the 3 target words, and then you have to generate a sentence containing those words. And now we have this new data set called contextualized CommonGen, where you have both the target words, your sentence, but also your context to which you have to adhere. So now we have the data set, but it would be nice if we can also evaluate this data set. So we have already some metrics, like Joey said, the automatic metrics and also 1 human evaluation. But it would be great if we also can evaluate whether our algorithm is following the context. And we didn't really find an automatic metric for this, so we went again to human evaluation. So the goal, what we did is we gave the sample to like humans and said, like, given this sentence, 5 minutes ago, Jacob went into the bathroom. And then we also gave the generated text. In the bathroom, he washed his hands with soap. We asked to the people, like, is this generated text a continuation of the context? And then they could just answer yes, no, partly. And we map it again on numbers such that we can have like a quantifiable metric. But it's very important, like this is a very obvious yes, because it's like it's a perfect example. But maybe this is a bit more tricky. It's important in this metric, we only put like underline the fact that should be continuation of the context and not logical, because that's our other metric. So in this case, 5 minutes ago, Jacob went into the bathroom, and in the bathroom, the soap washed him with a hand. It's like, it's not really, it doesn't make sense, but it follows the context. So in this case, it's actually a correct example. So this is then, but this is then a wrong one, because 5 minutes ago, Jacob went into the bathroom, and washing your hands with soaps helps to avoid the spread of diseases. It's like perfect. It's a perfect sentence, but it doesn't follow the context at all. So this is then like no. So these were then the baselines, and so this was the data set and the metric we're using. And now I will quickly show the baselines again and how they can use context. So he showed before like these three big groups of baselines. We have the training objectives. Those need to be fine-tuned on specific tasks. So we won't change this to our new data set because then we have to refine-tune the models and we didn't do this. So I will go into decoding strategies because they're easy to adapt and they kind of naturally have context in them. And then prompting will see a small problem occurring. So going through like the decoding strategy methods, as Joey said, you have like your context or input text. And then based on this, you will get a distribution to predict your next word. So you'll sample your next word from this distribution. And to make it controllable, you will skew the distribution so that more likely will contain the words you were asking for. And so you have your next word. So in this sentence, like in this like setup, it's logical. You can just replace your input text by context, and we have included our context. So it's like very natural. And in this sense, both algorithms, so this is the evaluation on our contextualized CommonGen, they have about the same performance, 75, which is good. They can handle performance well, and we even see like coverage, that when we give them some context, they cover more, so they get better at coverage, which kind of makes sense because the context was about to induce those words that we wanted to add. But still, they're not perfect because PPLM still has a very low coverage. It's still not good enough to be acceptable. For example, given this 4-5-word band machine pull repetition string, it is able to generate the concert had the most beautiful music. It was the first time I saw the symphony and I'm very happy I came. So it's perfect, but it doesn't contain any of the words. And then we go to key to text. Here also, it's great at coverage, but still bad at like performance. If you have the words bed, dog, nap, take, it will go like, I'll take a nap in bed and then I'll go dog free for an hour or so. And then I'll go dog free again for another hour, which no, not really makes sense. And then the last algorithm, which is GPT-2, where we did like this prompting with word inclusion, and then you have to start generating your text. What we'll have to do now is we'll have to like squeeze in the context. So you have like your examples of word inclusion, then you have your context, and you then start generating. But this makes that there is like a distance between when you start generating your text and your prompt. So we call this positional variance. And as this distance increases, it's like having less influence in your generated text, and it's very much less likely to occur. And this is also clearly visible. So the context is still fine because GPT is also very good at taking context into account, was also visible in Joey's example. But then the coverage drops both in free text and single text, which is not great if you want to do controllable text generation. Perplexity and common sense still is perfect for GPT-2. So we have like the words ball, that, day, fence, watch. And then the algorithm creates Sam's father answered the phone and asked him what he wanted to do, which is a great sentence, but again, bad at coverage, word inclusion. But we think we found some solution for this, but I will leave this to Fredrik.
Nice. Right, so although prompting is doing bad, we still think like prompting is the way to go, right? It is the current paradigm, we see it everywhere, and it has a lot of, nice properties. It's very expressive and versatile. We could do a lot of different stuff, right? We can do sentiment, we can do word inclusion, all of this. It's also usually plug and play, meaning we can just take a language model, train a language, and start prompting it with whatever, right? However, as Severine pointed out, we have this positional variance problem we need to figure out. But there's also actually another problem which we also need to figure out, and we're going to refer to this as residual instructions. It is less obvious, but let's go through it. So when we have our language model and we might have prompt in the beginning here, and we start generating, we sample a word. Okay, great. Now, at the next step here, we're going to have a hidden state in the language model, which will be attending to the prompt, meaning that this hidden state is going to be influenced by the prompt instruction. Potentially not bad, but as we do this, we figure out that, okay, we've now changed the internal hidden state of the model to include that prompt instruction. Like, it will have a residual effect potentially. And if we now want to, let's say, change the instruction, or maybe just start generating text that has nothing to do with the instruction, that information is now included within the hidden state. So we have this residual instruction effect. And potentially, this could become a problem, right? Let's say that we want to steer it with fine-grained control, and we start with the first prompt. Include the words captain, glare, and coast. And perhaps the language model spits out, the captain idly glared towards the coastline. And then we figure, you know what? Now I want it to have a sad sentiment here. And maybe it works. Then it says, then suddenly she found herself struggling to hold back tears of laughter as a rainbow-colored fairy popped up with candy, right? So maybe the next instruction will actually contradict the previous instruction, right? And then we really don't want to have this residual thing going on, because if we started with sad, and sad is now included in the hidden state, when we go for very happy and start generating, we could definitely have a problem here. So I would also like to add, you can also have a textual problem. Imagine having a bunch of instructions and they just accumulating. The hidden state of the model might all of a sudden not be super great for just normal language generation. So this is something we would like to overcome. And potentially one way to do it, if we have a new instruction here, is just to say, you know what, let's just scrap it. We just recompute everything with the new instruction. That is one potential way you could do it. The problem, of course, is that every time you switch or every time you want to remove an instruction, you need to recompute all the hidden states. So if you've generated a book up until that point, you need to recompute the whole book. It's still just one forward pass potentially, but it gets kind of tedious, right? It would be neat if we didn't have this residual instruction property. So we think that the solution for this is detaching the actual prompt from the language model. So we kind of have this intuition, right? The positional variance here, you see that it would be kind of nice just, be able to always have it tagging along. We don't want it to be able to, have a distance between the prompt and the current generation point. So the intuition here that, wait, how about we just actually cut it off? We have said, okay, you know what? We're going to have a new model for the prompt instructions. And we'll call this the prompt model, right? And the intuition here is that now this distance all of a sudden is compressed. We could say that we want the prompt model, so we'll train a new model that is going to generate positionally invariant prompt instructions. So we're going to have to figure out a way to train a new model that generates prompt instructions that is equally attendable at any arbitrary time step. And the way we do this is that we say we have a long training text, and we can generate multiple prompts at arbitrary points for this. And we just train the model now so that at the first part of the text, it is allowed to attend to the first prompt. At maybe the second part, maybe say second sentence, it's allowed to attend to the second prompt, and so on. Now, this does not solve the residual instruction problem. As you see, we still have this adding more and more stuff to the hidden state here, but potentially this alleviates, the positional variance problem. So the idea here is that fine-tuning the prompt model so that each instruction is equally attendable at any time step. That is the idea. Now, to solve the residual instructions, we figured out something else. So now that we have detached encoder and decoder, language model and prompt model, we now have this new attention schema. And I will try to explain this as pedagogically as I can. So think about a normal language model. We have the hidden state. Hidden state is like one word, yada, yada, per time step. We now introduce a new set of hidden states. So per word, we will have two sets of hidden states. We will have the normal textual hidden states that we always have. And we're also introducing something new, which is called the non-residual hidden states. Or we can refer to these as streams. So the textual stream and the non-residual stream. Now, the textual stream is just as before. So it's a completely normal generative language model. It is only allowed to attend to the previous steps from the language model. Note that it is not allowed to attend to the prompt here. It is only attending to previous textual steps. Meaning that at the first word, you only attend the first word, second word is allowed to attend the first and also itself, etc. Just like we normally do in next step prediction. Now, the non-residual stream, however, is allowed to attend any previous textual step and also the prompt instruction. So the first step, it is only allowed to attend to itself. There is no previous textual step. But at the second non-residual step, you can attend both the prompt instruction and also the previous textual step. Note now that we have no lingering prompt effects in the textual stream, because the textual stream only attends other textual streams. So the effect from the prompt is now non-residual in the non-residual stream here. So at any step in the non-residual stream, we only attend previous text steps and also the current prompt instructions. Meaning that if we now, want to introduce a new prompt instruction, let's go for an example. Okay? So let's say we have the instruction very happy and we have the context I. So for the first step, we have the textual stream, just as before, nothing new. Same for the non-residual stream. And now the trick is that we will actually generate text from the non-residual stream, meaning that we can still skew the distribution and the model can plan all of that while attending to previous context. So now we'll actually take the distribution from the non-residual stream, sample something, maybe it becomes really, okay, that's great. Next step, we input it into the textual stream, we attend previous I, we go to the non-residual stream, it also attends the previous I, gets really, but it's also allowed to attend the prompt here. And since it's very happy, perhaps it's going to sample like. And I really like candy. And as I said before, right, the big idea with non-residual attention is that we alleviate the need of, or the problem of having these residual instructions. So now we can actually just change the instruction, and at the next decoding step, the previous instruction is remained in the non-residual attention, but we'd never attend to that. So I hope that made somewhat sense. There's a lot of more equations in the paper if you want to read that. So just to recap, we have the two problems of positional variance and residual instructions. Our two solutions to this is one, the prompt encoder, detaching the prompt instruction from the language model. The second is having a non-residual attention schema when attending to these instructions. So now let's talk a little bit about what we actually did. So another clever thing I would like to point out is that when you create this prompt model, if you initialize it with the same weights as the language model, it will, by definition, have been pre-trained to communicate with itself. That is what a language model does, right? Like earlier steps in the language model are trained to pass information to, subsequent steps. So if you do this, you initialize by having a language model and saying, I'm just going to clone it and split it. That initialization step saves you a lot of training time. Now you only need to fine-tune the prompt model to be positionally invariant. It doesn't need to, learn from scratch how to communicate with the generative model. It only needs to learn how to be positionally invariant. So we say we clone it. Now let's talk about experiments. What type of prompts did we use and all of this stuff? And as both Joe and Severine pointed out, we went with word inclusion because it's actually one of the few controllable text generation subfields where you can actually have a good automatic metric, which is coverage. So we just took a lot of data, started splitting it up into sentences. For every sentence, we split it up into words. And then we say that, let's sample some of these words, maybe 2, maybe 3, maybe 4, maybe 5. And then we use that for the prompt for that sentence. Then we're able to reverse this to say, okay, now we have the long training text data, and now we have prompts at different steps. And the prompt is then going to be like, oh, here, now you're going to say a sentence. I want you to include this word or this word or this word. So now we can take this exact thing, reverse it, take the training data as input, and take those prompts to the prompt model. And, the output label here is still the training data. So you're still going to predict the next word, but you now have these prompts that tell you like, oh, in the next sentence, I want you to include the words A, B, and C. Now, we use Wikipedia for this. So we just took a bunch of articles, English Wikipedia, and we then started doing this thing with the sampling. So for example, if we have the sentence, the captain idly glared towards the coastline, we might sample the words captain, towards, and line. And that gives us the prompt, include the words towards, captain, line. And the label is then to generate the sentence, the captain idly glared towards the coastline. Now, this is what we did, right? We cloned it, we did the training, and I think we did about 1 epoch through Wikipedia. So it's not super much compared to, big pre-training corpora. So that is due to the whole initialization thing. Another thing we did is that we froze the weights of the actual language model. And this is because the model is already trained to generate good language. And we can see that it has good fluency. The problem was that we couldn't control it. So our ideology here is that we don't want to mess with the existing language model. Unlike, for example, PPLM that actually fine-tunes the weights of it, we think that, oh, great, there's a lot of good language models out there. We just want to be able to control them. Hence, we freeze those weights. And this, again, is a recap. We have these 2 data sets. We have the CommonGen, which has no context. We have our new data set, contextualized CommonGen. Let's start with that. And the results are pretty okay, I would say. If we start looking at the coverage, we see that I would say we're doing pretty good in the free text setting. So keyword to text, as you saw earlier, it had the highest, wasn't really the best text quality, but we even managed to beat that, and we're doing pretty good. Same in perplexity, we have a really low perplexity. I'll show you some examples later. We do, however, see that self-blur is higher, meaning that our model is less diverse than both PPLM and keyword to text. Why this is the case, we don't really know. It could be that we only fine-tuned using 1 corpora. So we only have like GPT, Wikipedia style text. Common sense, it does a little bit worse than GPT large plus prompting. And it's worth noting out here that all of these methods here are using the same language model. All of them are using GPT-2 large. So the reason why we probably have a lower sense is that we're focusing so much more on the coverage task. So GPT-2 large has a slightly above 50% coverage only. So it probably has a little bit more focus on, generating sensical text. We see in context that we don't really improve or become worse than any of the other methods. It remains about the same, but we have a 98.6 coverage. If we look at the single sentence, we can't use PPLM and keyword to text, as Joey mentioned, but comparing to the prompting, we do a lot better again. PPLM is better, self-blur is better, which is slightly weird actually. Didn't we have worse self-blur here? No, okay, it's about the same compared to GPT-2 large with prompting. Common sense is now about the same, and context is better. So this is a little bit, I don't know if we ever figured this out, to be honest, but if we just compare with the previous GPT-2 large with prompts, for some reason that one is better in the single sentence on sense, but the context becomes worse. And I'll be honest, it's not super clear what's happening, right? But at least we're not like horrendously bad, right? So And let's move on to, the normal CommonGen where we now have no context and see how we stack up against the previous algorithms. So right off the bat, we can see that we have a pretty good coverage when it comes to the free text setting. You just generate 32 tokens and we have 99.5 or 98.4, depending on what decoding scheme you use here. And it's not really that much to say. Again, we're better in perplexity. Our self-blow is again higher. And the common sense is about the same as a common GPT-2 with prompts. But for some reason, PPLM does better here. It's a little unclear why, but it also completely misses the task of coverage. So, however, in the single sentence, we have the KG-BART, which is specifically fine-tuned towards this very task. It includes a knowledge graph, as we said, and it has a slightly higher coverage. It does, however, do a little bit worse on the fluency of the text, it seems. Self-blur, again, hard to interpret, but we can see that we're way more diverse than the just prompted GPT-2. And the reason why this is probably that the prompt always includes a bunch of examples, and those are always the same examples. So probably the normal GPT-2 with the prompt is being skewed by the, prompt examples towards a certain type of language. In sense, this is where, KG-BART shines, because it has this knowledge graph, so it's probably not going to do a lot of weird stuff, like say that, hand washes the soap or whatever it was, right? And we see that we tend to generate longer sentences than the other. This will become obvious if we look at the KG-BART and our algorithm. We can see that, for example, a scooter rider wears a t-shirt that says, "I ride on the back." While the slightly shorter sentence from KG-BART, "A man is riding a scooter and wearing a shirt." So this is basically the stylistic differences between the two top contenders here. KG-BART is, very much to the point, doesn't really do anything too nice, but it really usually is commonsensical. Another example could be the player presses a button on the scanner to place the card in his or her inventory, versus a woman presses a button on a scanner and places a card on the scanner. So some stylistic differences, nothing's better, nothing's worse, just a difference. Now, before we run out of time here, let's just skim over some additional experience within experiments. So when you have this self-supervised data loop, we will create the prompts from the text data. We realize not only can we sample words, we also have this information of sentence length. So maybe we can actually train the prompt model to also generate instructions for sentence length. So we take these sentences, for example, the captain idly glared towards the coastline again, and we take not only some sample words from it, but also how long the sentence is. So now we actually tell the model, okay, the next sentence you're going to generate, use 8 words, and I want you to include the words towards, captain, and line. And what this gives us is that it gives us another stylistic tool we can use. So we can actually have the word drink, sit, table, and wine, but we can prompt it with some different lengths here. So if you say, I wanted to use 6 words, I wanted to use 12 words, and I wanted to use 18 words. And the text that comes out is quite different. So the wine drinkers sit on the table, the guests sit at the table and drink wine or beer. The guests sit at the table and drink wine while the hostesses sit on the floor, right? You can really see that we're starting to expand upon this. So it still is the same word inclusion, but it quite changes the stylistic tone of the model. And yeah, if you want to do something more controversial, perhaps you want to say amazing, Trump, politics, victory. And yeah, you also get these, potentially controversial stuff, right? And if you're interested in how well it, you can also notice that it doesn't necessarily stick to the prompted length. See that sometimes it does shorter, sometimes it's longer. We prompted it with 20 words in the final example. It actually generated 25 words. So we have this tendency of preferring to stick to, including the words and actually finishing the sentence with some kind of syntactic sense. And we tend to find that it, on average, generates slightly longer sentences. So what you see here is the offset. The filled in line is the mean of the offset. So if we prompt it with 20, it is likely to generate slightly above 20. And the standard deviation is quite high. So it doesn't really stick to this spot on. You could probably train it. Now, everything I've told you so far is a lie, because unfortunately, we don't have the biggest computational resources. God, I wish we had, but we really didn't. So we had to cut some corners in this, actually. So one thing, as I mentioned, is that we froze the weights of the GPT-2 large, but we still need to have 2 models in memory. So when training these models, the memory complexity on the GPUs easily gets quite high here. So although we freeze the weights, meaning that we don't need to have an optimizer state for the generative model, we only need to update the prompt model there, we still have a problem with the amount of context we can actually train over. So preferably, we would just take 512 tokens, press it in there, update the prompt model towards all of them. But yeah, out of memory errors every single time. It was a nightmare. So we decided, okay, let's just go down in context length. And we kind of discovered that we could only do this for single sentences, which kind of, ruins the idea of like, oh, we want to train with context, but if we can only do one sentence, we're kind of stuck there. So the hack that we invented for most of the experiments is that we actually freeze the prompt model as well and only train it on single sentences. So we train the prompt model to do single sentences, we update it, it becomes really good at word inclusion, not at context. And then we freeze that model as well, introduce a new transformation, which is just a linear transformation of the prompt model to make it positionally invariant. So I would prefer to not talk about this because I think this is a really ugly hack, but it works. So in theory, we would just fine tune the prompt model to become positionally invariant. But what we had to do in reality was that we trained the prompt model to do word inclusion, and then we did a positionally invariant transformation of that. So this is all due to memory complexity. So please don't ask any questions about this. Let's ignore that this exists. Right. Yeah, and this is basically what you end up with. So I don't know if I have any time left, probably not, but go ahead. Okay. Well, I have plenty of slides. So, just to give you an idea what this could be used for. So keep in mind that the texts you've all seen are from very, very small language models compared to today's standard. This is all using GPT-2 large, not even the biggest GPT-2. And as we all know, size matters. So it really doesn't hold up in linguistic skills to the newer models. But something we are now working on is that together with Eleuther, we're going to try to take GPT-J and make it controllable for word inclusion. Of course, some interesting things you could do, which is not word inclusion, right? We have this talk about maybe we want to steer the narrative, maybe we want to have sentiment, there's a potential plethora of stuff you might want to be able to steer. So you could also say that maybe you want to have a different type of prompting scheme, introduce the character Anna and maybe say that, now you want to have green eyes and talk a little bit about the environment and all this stuff. So we have these ideas of creating prompt data sets, self-supervised using, parsing and stuff, and just somehow get other stuff into that prompt model, like not only word inclusion, maybe sentiment and all this. So there's a lot of potential you could do with it. We haven't yet figured out how to do it, yes. So maybe you want to have something more very data to text. Maybe you're really into wow, you're creating news, whatever. It's really important to say Afghanistan and not India. right? It's really important to get the data in there. Then you can also use something like this to be like, okay, well, in the next sentence, you should really say 2 deciliters of sugars. If you say 2 liters, we're gonna have a really sweet cake. So, the idea of this non-residual prompting is not confined to word inclusion. So I just want to separate those two. And I think that's it. Thank you all for listening to all the great speakers.